So, consider the function f equal to a plus b c when it is realized in canonical product of some form, and this is the realization. Okay. Now, suppose this a b c all of them are at 0. So, what has happened is that all of them being at 0. So, here this OR gate all the 3 inputs are 0. So, this output is 0, and this OR gate, this has got some of the inputs as 1, like when b is 0. So, this input is 1. So, this is 1, and similarly this is also 1, because this input is coming here as 1. So, this AND gate output is equal to 0. Now, consider the case when this C value, it has changed from 0 to 1. When it has changed from 0 to 1, so we have when this C value has changed from 0 to 1. So, this output is the C input has become equal to 1. As a result, this OR gate will now be equal to 1. So, this output becomes equal to 1, and after some time this inverter output will be activated. So, inverter has got some delay. So, before the inverter delay was activated, so this OR gate was remaining at 1. So, you are getting some output, but now after some time this inverter will be equal to 0. As a result, this OR gate value will become equal to 0. So, this F3 will be equal to 0. Okay. So, this way, due to the presence of this delays of the inverters, okay, so this circuit will produce a glitch at the F3 output. Okay. So, this similarly this F1. So, F1, suppose this A, B, C, the A is 0, B and C are 1. So, this is the situation, the F1 output is equal to 1, and now if there is a change that B and C become equal to 0 and A changes to 1, then what will happen is that due to the delay, so the effect will not come immediately. So, F1 will be remaining as equal to 1, and now it will become equal to 0, and then after some time, see B, suppose this inverter of B, it changes its state. So, it is getting 0. So, it will be getting it will affect the circuit after that. So, this way, so if you look into the gate delays if you take this gate delays into consideration, you may find some behavior of these circuits in some intermediary form. Okay. So, that is not stable actually. So, in between it shows some glitch. Okay. So, that can happen. So, it is just, you can just trace through this circuit to see that this is changing the value. Okay. So, whenever it is red means it is going to logic 1, and wherever I am showing it by black line means it is at logic 0. Okay. So, you follow that convention and trace through these diagrams, then you will find the implementation this creation of the glitches. On the other hand, these dynamic hazards, so they occur when a literal assumes multiple values. Okay. So, through different paths with different delays, they have got different values and causes an output to toggle. So, as we have seen, the output should go from 0 to 1, but in between it makes some toggle, or it goes from 1 to 0, in between it makes some toggle. So, consider this circuit that has got this A, B, C as input, and this suppose this B value. So, suppose situation is like this, that A is at logic low, C is at logic high, and this B point at B1, it changes state from 0 to 1. So, at B1 it changes the state. Then what will happen? So, B2, so at this point, so there are 2 inverters from B1 to B2. So, after 2 inverter delays, so B2 will show this waveform, okay, at this point. Then at B3, so B3 has got so A is at logic low. So, for this NOR gate, so it is nothing but an inverter. So, this B3 is at so B1 sees the delay of this NOR gate plus this inverter to produce B3. So, that is if I assume that this NOR gate has got delay equal to 2 inverters. So, after 3 delays, so or after So, they are having some same delay. So, NOR gate and this inverter they are having same delay. So, after 2 gate delays, so B 3 gets the value of B 1. Okay. So, B 1 has changed from 0 to 1 and B 3 has changed from 0 to 1 after 2 gate delays. Now, when it comes to this F, okay, and this C is always 1. Okay. So, C is always 1 means this NAND gate it is always giving B 1 bar, and then this is giving me the whatever is coming here depending upon this B 2 value. So, this output of the NOR gate is coming. Now, if you trace this circuit again, you can find that the situation will be like this, that initially the F will be high, it will show be low for 1 gate delay, then it will be high for 2 gate delays, and then again it will be low for the remaining part of the system. So, that way, so there is a glitch. So, this is a dynamic hazard here. So, here it shows a dynamic hazard at this point. Okay. So, there is a dynamic hazard at this point. So, you can just trace through this circuit and see that this type of timing diagram, these waveforms are appearing, and that creates the dynamic hazard. So, this has to be avoided. Now, how do we do that? So, this is the dynamic hazard. Now, how can we actually these dynamic hazards are difficult to remove. Okay. So, we will be talking about static hazard first. So, the key idea for eliminating static hazard is that the glitches happen when a changing input spans separate K map encirclements. So, if some if you are going from say this box to this box, okay. So, you are changing some input so that it goes from this circle to this. So, in between it may go through some 0 state, as a result the circuit output may become 0. So, that is the key point. Okay. For example, so when you are going from 1101 to 0101. So, 1101 is this one, 1101 is this one to 0101. So, 0101 is this one. Okay. So, whenever you are going from here to here, so it may so happen that this delay comes. So, A is delayed a bit and then this 1 to 0. So, that delay takes some time, and in between it goes to this 0 state or this 0 state, and that way it creates a it creates a glitch. Okay. So, how to solve this? Sorry. So, how to solve this is something like this, that so this is the situation, like say we have got the function. So, this square it represents A C bar, and this other quad it represents A bar D. Okay. So, it is A C bar plus A bar D. Now, if I have got the situation like A B C D is 1101. So, you get this 1101. So, A and C bar. So, A and C bar are 11 and A bar and D. So, that is 01. So, it is applied here. So, you get 1 and 0 here, accordingly the output is 1. Now, it is changing to 0101, but this A changes and it takes some time for A bar to change. As a result, you may find that it will produce a 0 in between. So, that 0 has to be avoided. How to solve this is that we add some redundant K map encirclements. Okay. So, we add some extra encirclements. So, like this. Okay. So, so that the single bit changes can be covered in the same block. Okay. So, it will eliminate static 1 hazard. So, using sum of product form, and this if there is static 0 hazard is also there, then we have to use the POS form, product of sum form also. So, use this. So, first of all, so the process becomes complex. First of all, you do encirclement and make the SOP form, and then if you find that this static 0 hazard is also there, then you have to use this product of sum form and again do the encirclement in that fashion. But unfortunately, this technique works only for 2 level logic. So, multi level logic there is no solution to the static hazard problem. So, this is so that if it occurs, so you have to be careful there. So, this is an example. So, how do we do this? So, same circuit, that A C bar plus A bar D. Okay. So, what we have done? We have done some redundant encirclement. Okay. So, this C, so this was this red one, this red quad was not necessary, okay, because we have all the ones are already covered by the remaining 2 quads, but we do not but we take this redundant one. What will happen is that even if this A is changing the value, okay, this C bar D, so this will hold the output. Okay. So, this the problem occurred because for some amount of time this A and A bar both of them were equal to 0. As a result, this OR gate input both the inputs were 0, but this C bar D. So, C bar D term has been added. So, C bar D does not make a change. So, C bar D holds the value at 1. So, it will be you will be getting a 1 if we are changing the input combination like that. Okay. So, this way we can eliminate the static hazard by doing some redundancy. So, we are going a bit counterintuitive, like for Boolean function minimization. So, we do not allow this type of extra quad or square formations, but in case of for eliminating the static hazard. So, we are doing the other way. So, we are allowing these extra terms, so that these hazards are not there. So, we can eliminate static hazards in 2 level logic for single bit changes, and eliminating static hazards also eliminates dynamic hazards. So, that is one good thing, that if we eliminate static hazards, the dynamic hazards will also not be there. So, that way it is useful. Hazards are a difficult problem. So, multiple bit changes in 2 level logic are hard. So, we are whatever example we are considering. So, we are considering only a single bit change. Okay. So, if the multiple bits are changing, so it is difficult to solve that type of hazards, and static hazard in multi-level logic is difficult, and dynamic hazards in multi-level logic are it can say it is yet more harder. Okay. So, that way it is difficult to solve this for multi-level circuit, this dynamic hazard problem. Next, we will be looking into a few examples of this combinational logic design. So, suppose we are the first example, we are determining number of days in a month to control some watch display, and it is used in controlling the display of a wristwatch LCD screen. Inputs are month, leap year, month and leap year flag, and outputs are the number of days. So, you give the month and the leap year flag, it will output the number of days in it. So, if I have a combinational circuit, I have to design a combinational circuit where month will be one input, and whether the year is a leap year or not. So, that will be coming as input, and it will be outputting the number of days in the month. So, this is a typical example. See, we have got this month can go from January to December. Okay. So, we did this month is a 4 bit input, because there are 12 months. So, I can have I need 4 bits for encoding these 12 months. Okay. So, 4 month bits are coming, and leap year is a flag. So, this leap year, if it is it may be 0, it may be 1. Okay. So, this is the final block that we are designing. Okay. So, here you see that we have got as input this 4 bit month and leap as input, and there are 4 outputs 28, 29, 30 and 31. So, if it is 28 day in that month, then this output will be 1, rest will be 0. Similarly, if the number of days in the month is 29, then this output will be 1, rest will be 0, that way. Similarly, 30 and 31. So, if we look into the truth table, so it is like this. So, here the month is 4 bit. So, if it is so our month will start with January. So, we are assuming that we will be entering 1. So, 0000 is never given as month. So, for that I do not care the output. So, for 0000 whatever be the leap year value, so output need not be considered. Okay. So, that is do not care. Then 0001. So, if it is again the leap year need not be considered, leap year is do not care. So, it is 0001. So, it is a January. So, 31 day month. Then this 0010 is the February. Now, I have got the leap year, this is without leap year and this is with leap year. So, in with leap year 29 will be a high, and without leap year 28 will be high. So, it goes like this. So, this way I can draw this table. Now, this one 8. So, this is my month 12 December. So, this is accordingly it is 31 month. Then so, this is 1101 and 1110 1111. So, they are all do not care, because we do not have 13 14 15 months. Okay. So, they are all do not care. So, this way I can make the truth table. Once you have made the truth table, so you can write down the corresponding combinational function. Okay. So, 28 is M8 dash that is M8 bar, M4 bar, M2, M1 bar, leap bar. So, 28 you see that 28 is 1 only for this combination. So, this all these bits M8 bar. So, this is M8 bar, M4 bar, M2, M1 bar and leaf bar. Similarly, 29 is for this, 30 is. So, these are the corresponding logic expressions. So, what you can do for getting this, you can draw the corresponding truth table. From this truth table you can make the corresponding Carnot maps and do minimization and get the logic function. And then in terms of logic gates, so you can realize this combinational function. Next we look into another example, which is BCD to 7 segment display controllers. A 7 segment display is quite common. So, you can find many such displays on the roads and all. So, here we have got so actually these 7 segments are there. So, each segment is a light emitting diode. So, you can control it to be high or low, you can turn it on or off. Okay. So, for that I have to give a 1 to that segment. So, that the segment will be turned on, and for making it off, so 0 should be given. Now, normally we want to display the digits 0 to 9. So, we have got a 4 bit binary coded decimal digit. So, and this value is coming here, this ABCD is the 4 bit binary BCD value that we are having. Now, based on this input, so I have to select the appropriate segment. So, these segments are named as C0, C1, C2, C3, C4, C5, C6, the 7 segments. So, for example, if you give 0, then excepting C6, all other segments should be turned on. Similarly, if you are giving 8 as input, then all the segments should be turned on. So, I can draw the corresponding truth table like this. So, for ABCD equal to 0 0 0 0, so C0 to C5 all are 1 and C6 equal to 0. And similarly, whenever you are outputting, say for 8 1 0 0 0, so we have got for 1 0 0 0 we have got all inputs, all the segments to be turned on. So, we have got all 1. So, for 9 we have got this, for 10, 11, 12, 13, 14, 15. So, they do not care. So, I do not have to do anything. So, for getting the corresponding implementation, so you have to draw the corresponding Carnot maps. So, these are the Carnot maps for the different conditions. Okay. And then, so these are the corresponding Boolean expressions, so C0, C1, C2, C3, C4, C5, C6. So, these are the Boolean expressions, and once you have these Boolean expressions, so you can realize them using the logic gates. Okay. So, that can be done. A better implementation can be like this, that there are 9 unique terms. Okay. So, if you are looking into this if you look into these functions, see this A is coming here as well as there. So, this then this say this B bar C. So, B bar C is there in C3 as well as in C6. Okay. So, in this way, if you look into the patterns, then many of these product terms are common between the functions. So, so this is the situation. So, this B bar C is common and all. So, what we do, we can modify it so that this is this commonality can be used. Okay. So, this commonality can be used. So, that way I will have less number of terms. Okay. So, less number of terms will be realized. So, this so, they will share the number of outputs, and then of course, each output is not in minimized form, like you see that here we have got so this B in this C0 it was A plus BD plus C plus B bar D bar, but we have modified this A, so that C0, so that the expression becomes like this. That is, we do a grouping so that it is not the optimal one, but what has happened is that this B C bar D is shared between C0 and C3. Similarly, this B bar D bar is shared between, say, this C0 and this C3. So, that way we can make these terms common between these multiple outputs, so that total number of unique terms becomes less. Okay. So, this is actually a combinational logic minimization problem, and for multiple outputs, this is a very difficult problem in fact, and there are many CAD tools that are available which does this type of optimizations, where it tries to share terms between the logic functions to get the minimum number of product terms for the whole function. So, whatever minimization technique we have learnt using Carnot map and all, so they are for single output functions. So, whenever you have got multi output functions, then there is a goal to share between the share the product terms between outputs, and this is one such example where we see that if we group in a different fashion, then for example, this C 2 instead of grouping like this where we are getting say B plus C bar plus D. So, in this type of grouping, so you will get C 2 as a term like this, but the good thing is that you do not need any new term. So, for example, this B bar D is there in C 1 also, C bar D, so the B C bar D is there in C 0 also, C bar D bar is there here also, C D is also there, and then B C D bar is also there in C 0. So, as a result more number of terms are getting shared. So, using only 9 unique product terms, so you can realize all the functions C 0 to C 6. Okay. So, that can be done. Next, we will consider another example which is production line control. So, we have got some rods with of varying length that travel on a conveyor belt. Okay. So, the length may vary, the length of the rod at the production site. So, it can vary between plus minus 10%, and mechanical arm pushes rods with specification plus minus 5% to one side, and the second arm pushes rods too long to the other side. So, what is the rods are produced with an accuracy of plus minus 10%, but we want the rods to be on the proper specification. So, we will have this thing. So, this is the specification. So, this is within specification. Okay. So, this is within specification. If the rods are within specification, then it will pass. If the rods are shorter, okay, so that is too short. So, they will be taken out by this on this line, and similarly, if the rods are larger like here, so it is too long. So, then also it will be taken out. So, A to B distance is the specification minus 5%. So, A to B distance is specification minus 5%. So, any rod that passes through this AB, so that is actually not acceptable. Similarly, A to C distance is specification plus 5%. So, that way that is also not acceptable. So, anything between this plus minus 5% is acceptable, but otherwise it is not. So, for this one, if ABC is 0 0 0, so that is basically this ABC. So, they are, so it is not violating any of the conditions, then we do nothing. If it is 0 0 1, that is it is not this A and B are 0 0 and C is 1, then also it is do nothing. So, only when this A is equal, if A is equal to 1, in that case the rod is too short. So, output is too short, and then if it is 101 is again do not care or do nothing, because that is a do not care condition. Then 110 is, this is a valid within specification, and 111 is too long. So, I can write down the corresponding logic expressions for too short within specification and too long, and accordingly we can get the corresponding function. Okay. So, I can have a combinational logic. So, based on these A, B, C outputs from this rail. Okay. So, from this rail, so we can identify whether the rod is within specification, too long or too short. Another example, so we have got a multipurpose function block. So, this is there, so C 0, C 1, C 2. So, these are the control inputs, and there are two data inputs A and B. So, based on this C 0, C 1, C 2, so it will perform some function. So, for example, if C 0, C 1, C 2 is all of them are 0, so it is a constant function. So, irrespective of the values of A and B, so it will output a 1. If C 0, C 1, C 2 is 0 0 1, then it will compute A plus B. So, it is a logical OR of A and B. So, 0 1 0 is logical NAND, 0 1 1 is logical XOR. So, like that we have got different functions to be implemented if the C 0, C 1, C 2 are having some specific value. Now, so this is the truth table. So, this C 0, C 1, C 2. So, this is 0 0 0, then this A and B they are having. So, this is a constant function. So, irrespective of the values of A and B, output will be 1. Similarly, this for 0 0 1. So, this is the OR of A and B. So, this is the OR function is realized here. Then this 0 1 0. So, this is the NAND function, So, it is doing the NAND here. So, this way you can draw the truth table, and after you have made this truth table, you can do a logic minimization to get an expression for f in terms of C 0, C 1, C 2, A and B, okay, and that can give us the expression. So, so that can give, so that the final circuit is not shown here, but you can always do some logic minimization and get the function the logic the digital circuit implemented in terms of C 0, C 1, C 2, A and B.